InnovaWorld Research Center of InnovaWorld's Private Limited from November 4 to November 9th, 2024. This program marks a significant step towards equipping professionals and enthusiasts with advanced tools needed to transform industries, solve complex challenges, and push the boundaries of innovation. As India's first private research center, registered under MSME and established in the Hooghly district of West Bengal, InnovaWorld's Private Limited has always aimed to be a pioneer in education and research. Our journey begins with an YouTube channel inspired by visionary Dr. APJ Abdul Kalam and has since evolved into multidisciplinary research hub that focus on STEM, especially in the aerospace and aviation sector. Today, we continue to uphold the vision by expanding into emerging fields like artificial intelligence and machine learning, integrating them into sectors where they can create the most impact. I welcome engineer Aishwarya Dhara, founder of InnovaWorld's Private Limited, also the founder of CEO of Skyfi Tech, co-founder and director of TEMS Tech Solutions, and department coordinator, Department of Aerospace Engineering, GNA University. I extend a warm welcome to our Managerial Officer, Engineer Pomma Kishan, who is also the founder and CEO of Wings of Aero and advisory of TEMS Tech Solutions, whose strategically guidance drives our endeavors towards success. Furthermore, I extend a heartfelt welcome to Dr. Anuray Majumdar, our esteemed research head, who serves as the backbone of our research division. It is a true privilege to welcome a distinguished guest and visionary in this field of artificial intelligence and industrial engineering, Professor Arya Bhattacharya, to our skill development program on AI and ML in industrial engineering organized by InnovaWorld Research Center. Professor Bhattacharya is currently the Dean of Research and Development and a professor at Ecole Central School of Engineering, Mahindra University. His vast expertise is backed by over 20 years of invaluable industrial experience, having served in critical R&D roles across esteemed organizations such as the Defense Research and Development Organization, ADA Bangalore, Alstom Transport in the UK, and Tata Steel's Automation Division in Jamshedpur. His esteemed career in academia also includes his tenure as an AICTE INAE Distinguished Visiting Professor at Birla Institute of Technology, Mishra, where he contributed significantly to advancing engineering education. Professor Bhattacharya's impact on the field is profound, with over 20 patents filed and more than 40 research papers published in leading journals, international conferences, and book chapters. His work exemplifies excellence and innovation. His research spans an impressive array of fields: artificial intelligence, machine learning, deep learning, evolutionary algorithm, game theory, and autonomous system. He has successfully applied these cutting-edge technologies to critical domains including aerospace, manufacturing, industry 4.0, logistics, and supply chain and transportation. We are truly honored to have Professor Bhattacharya with us. His extensive expertise in bridging AI and ML with this industrial application aligns seamlessly with our goal for this program. His guidance and insights will be invaluable as we explore the transformative power of these technologies in shaping the future of industrial engineering and beyond. Once again, I welcome each and every one of you. Let me make today's session one to remember. Over to you, sir.
So, okay, thank you. Thank you very much for the kind introduction, although I don't think I deserve all those words. So I'll start sharing my screen. Before I do that, I'll just like to mention here that we have with us Mr. Kumar Chatterjee, who is actually a very experienced person in industry and also to some extent applications in machine learning. And he's the CEO of a company called MCAR Tech based in US, and he's also joining us, but I don't think he'll be able to stay the entire 90 minutes or so. So thank you, Kumarda, for joining us. Okay.
Once again, I welcome you, sir.
So shall I start sharing my screen now or wait for some more time?
Yes, sir, you can start.
Okay, thank you. So I would just like to state here that, well, like my presentation is, first of all, good morning to all of you. And of course, as I had a short chat with Madam Aishwarya yesterday, so she said that there'll be a lot of attendees. And of course, as she said, I'm not able to see most of them, just a few of them, but that's fine. So I would just like to start by saying that in this presentation, there are actually two parts. So the first part deals with, although this is the beginning of the presentation, but I'm going to start with something which is coming towards the last quarter of the presentation, which talks about generalities in application of artificial intelligence in manufacturing. Then I will come to a specific instantiation of this in a specific example, which I think you'll find interesting and also quite informative. So let me start. So here we're going to talk about application of AI in manufacturing. And okay, before getting into that, I think we should all first have an understanding of what AI implies. So in this diagram, you have got about, well, we have the outermost circle, which is artificial intelligence. And you see that it is colored blue, right? The border is blue. And that includes certain elements which are subsets of that bigger set. And those are some elements which are not within those smaller subsets, like knowledge representation, inference, logic, uncertainty, Bayesian techniques, game theory, and quite a few others. Rest of the matter, you see there are two elliptical subsets, you can say. One of them colored pink is machine learning, and the other colored green is computational intelligence. And you also see them overlapping, and in the overlap, there's something called as deep learning. Okay, so you understand now what is deep learning, which is flashed around the media all around the place. So here in machine learning, basically we are learning relationships or patterns or policies from data. And here we talk about classification, regression, clustering, dimensionality reduction, and so on and so forth. Computational intelligence are basically biologically and socially inspired techniques. You can say naturally inspired techniques, okay? So this involves areas like fuzzy logic, evolutionary algorithms, neural networks, and a few others. And deep learning is something which is dealing with neural networks and dealing with data. So it is the overlap or the intersection of computational intelligence and machine learning. Okay, let's proceed further. Now, I would also like to say that, generally, I think, the organizers have a policy that probably questions are only towards the end or something. So I don't want to violate that policy. But normally, as a teacher, when I take class, I tell my students that fire questions. Whenever you find something that you're not understanding, instead of keeping it in your stomach, ask a question. Okay, anyways, I think that will not work here based on the organizer's policy. All right, let's proceed. So first is application of AI in manufacturing. Let's look at high-level views. There are a number of functions in manufacturing where AI is making significant difference. We will discuss these one by one. So these first few slides that I'm going to read about, this is what I'm calling as by section 1 or part 1. This will mostly be reading through slides, and I'll be explaining as we go along. The second part will be about 2/3 of my presentation time, and that will be, as I said, a specific instantiation. Okay. So application of AI, there are a number of functions in manufacturing. So one of them is predictive maintenance. So what are these? So we have multiple sensors on equipment and machinery which capture relevant parameters and send to AI engine for real-time processing. AI uses a combination of supervised and unsupervised learning to detect anomalies in processed variables, their levels, trends, and types. So I have not discussed what are supervised and unsupervised learning. I think we'll skip that because if I start taking it, it'll be the whole day actually. Okay, the generated values from either of these two types of learning are used at 3 different analytical levels. At the lowest, it enables monitoring of all equipment and machinery. Point number 1. Point number 2, it predicts failures, their time in the future and their type, and hence enables corrective maintenance precisely when needed. And actually, when we predict failures in the future, that is actually called as prognostics. Prognostics is different from diagnostics. Diagnostics is analysis when something has already happened. Prognostics is predicting what is going to happen and when it is going to happen. Okay. Finally, it facilitates an optimal maintenance strategy across all equipment, personnel, and costs. And expected to reduce about 10% annual maintenance costs and 20% of equipment downtime. I would just like to add here by the side, I think I'm having it down the slides, that when we talk of prediction, we predict not only machinery, we also predict the condition of processes. We'll talk about these as we go along. Productivity and quality enhancement. So individual operating processes within a production chain in process or manufacturing industry can have operating conditions or operating regimes of high productivity and product quality, of low productivity and low product quality, accompanied by instability and various intermediates. Each of these regimes of operation are characterized by specific combinatorial relations between different running process parameters. And AI can, using unsupervised learning, extract these relationships characterizing different operating regimes, and B, using ANNs of different architectures, predict the incipient formation of these relationships in real time. By control and corrective actions specific to the domain of the operating process, the processes can be prevented from degrading to unstable conditions or taken to higher levels of productivity and quality. So here we are talking not only about processes that are going to degrade, and we are predicting in advance that the process is going to degrade and so take corrective actions. There's also an alternative that we try to find out what are the best operating conditions in terms of productivity and product quality. And also minimize, when we say productivity, also to some extent cost is incorporated in that, so minimization of cost. So also to find out what kind of conditions will have the highest productivity, highest quality, and best cost conditions. Okay. So the final product quality and productivity of the complete chain depends on optimization across individual processes, where the optimal process parameters can be extracted using multi-object. Okay, let me just stop for a moment. See, when I've used a phrase called, I hope my cursor is visible here. So when we say complete chain, see, most of the time manufacturing is not one single unit of manufacturing. It can be, but then they are very small conditions, okay? Or you can say small setups. Usually in manufacturing, we have a chain of processes starting with, say, some kind of materials and ending with final product with many transformations in between, and they are like the links of a chain, okay? All right, the final product quality and productivity of the complete chain depends on optimization across individual processes or links in the chain, where the optimal process parameters can be extracted using multi-objective optimization, and the individual processes run at optimal conditions using the above mechanisms. Okay, so we can have, say, for example, this is a diagram, just an illustration, kind of conceptual illustration. So specific studies undertaken in semiconductor industry have shown productivity improvements of about 30%. Another small point, which I think because we are dealing with manufacturing, we should be aware of, is that whenever you have manufacturing, you have got actually two kinds, broadly two classes of product. One is continuous product and the other are discrete products. So if you have semiconductor chips, or if you have steel plates, or you have cars, vehicles coming out, they are like the discrete products. On the other hand, if you have oil and gas mechanism or power being generated, these are continuous products. So you just keep this in the back of your mind. So as the figure shows, these are obtainable within an industrial IoT framework of Industry 4.0, which enable massive data flows in real time across sensors, networks, computing at edge and at cloud, and actuators. So you are trying to see here the geographically distributed production systems, connected industries, and you have material, equipment, process, product, everything. The entire thing is kind of supervised or controlled by AI, which recommends actions to achieve multi-objective optimization and machine learning through AI and through simulations. So that's the idea that I'm talking about actually. In many domains, these are accompanied and supported by digital twins, itself supported by IIoT. So digital twins is another very interesting concept, but again, I think I'll not talk about it at all, but then possibly this is a good topic that can be taken up in a series of lectures or a workshop like this. Okay, then we have another, so we have talked about, condition monitoring. We have talked about improvement of products and processes. Then we have automated quality testing. So automated product quality testing has been around for some time now, using non-destructive visual or like visual testing of products across a range of industries. So, like you see solar panels, steel strips, vehicles, and so on and so forth. Using AI, particularly deep neural nets like CNN, it is possible to test in the production line itself for defects by abstracting away variations due to light intensity and color shades, orientation, background, etc. So I don't know how many of you are familiar with CNNs. So CNNs is something in which you, number one, you do not need to do feature engineering. So, you put in inputs and it automatically learns which of the variables are more important, which of the variables are less important. And the other thing is that you can have a lot of variations. Say, for example, if there's an image of something, the image does not have to be of a particular type, of a particular level of intensity, and so on and so forth, or color or orientation and so on and so forth. All these things are learned by the CNN automatically. So this obviates the need to take away samples for offline testing, which delays the complete process chain and also ensures complete coverage of product and further highest accuracies. And CNNs have since 2016 beaten human accuracy levels in image classification. 2016 is quite some time back, actually. Many developments have taken place since then. This is expected to increase productivity by about 50% and ensure detection of 90% defects with significant downstream business benefits. Then we have improved supply chain management. Sufficiency of supply chain depends on accuracy of demand forecasts and supply constrictions, among other things, as well as near real-time prediction of fluctuating conditions caused by different factors. AI has the potential to significantly improve forecasting in supply chains using supervised learning, particularly Bayesian networks, which can be trained using archived data and also handle complexity induced by multiple known factors. Further, AI-based optimization techniques can quickly work out solutions in response to variations among these factors, and thus complete AI-based solutions can be created to predict and then optimally solve for supply chains. And expected benefits include significant 50% reduction in forecasting error, 50% reduction in inventory, and about 65% reduction in lost sales due to product unavailability. So these are things which actually impact the producer of materials because, okay, anyway. So now we go into something else, slightly deviant from what we have been talking about, suggested steps that manufacturing entities may take for AI implementation with maximal benefits. So I don't have a complete profile of all the audience, but this would be particularly relevant for those who are engaged in manufacturing industry and in the kind of operations management of manufacturing industry. So with the business benefits of AI implementation quite apparent, the obvious question is, how does one systematically implement AI company-wide for optimally achieving these? So for example, if you are, say, in charge of or looking after a complete production chain of some product, okay, whatever it may be, either continuous or discrete, as I talked about, you would like to see how you feed in artificial intelligence at different stages and extract the maximal benefits. The following 4 suggestions may be considered. Work out a few targeted areas within the entire manufacturing process chain where AI may be first implemented based on the discussed 4 application areas and possibly using the theory of constraints. Now, theory of constraints is something that was propounded by someone called Eliyahu Goldratt, and he has become very famous and is a consultant for a lot of industries globally. So the basic idea of the theory of constraints, cutting out all the other things, is that if you have a chain and if we have, say, at each chain, and you want to maximize the productivity of the throughput through that chain. So the first thing you should do is find out which is the number 1 point of constriction or bottleneck, okay, and work around it so that that bottleneck or constriction is removed or expanded, okay. Once that is done, your potential or capacity of your chain has improved, and then it goes and gets stuck at the next bottleneck or constriction. So work around that and expand that constriction. So that is the way this theory of constraints is supposed to work. Okay. So for any suggested area, the AI expert and the operations engineers must work in sync, and each should be made aware of the specifics of the other for best integration. Now, this is a very important thing. You see, one cannot really implement AI gainfully by just having an AI expert and giving it to him to try to improve a process, because a good deal of domain insight is needed for improving the process as well. So in the example that I've deliberately selected, you'll find how much important it is, both for the AI awareness and the mathematics and the theory behind it, as well as for the domain expertise, which only the domain expert will be aware of. And only if the two work in sync, that will really expect some breakthroughs. Okay, if the operations engineers alone, they're told they'll learn AI from somewhere, they'll not be able to do it also by themselves. Okay, data is a critical player, and traditional relational databases will hardly help in the Industry 4.0 framework. One has to move to, I think this is now well known, like you heard of big data and things like that. So one has to really move on to NoSQL-based frameworks. And then aim for agility by first using simulation-based pilots, which enable faster convergence to meta hyperparameters of the AI system design, followed by online plant validation trials in safe parallel mode, and finally implementation. Usually in a running process, no one would like to take the risk of implementing a new system when the system is apparently going well, but one wants a further improvement. So in this case, one actually creates a parallel implementation where the actual control or monitoring is done by the existing system, but then the AI-based system is also put in place so that one can actually compare how the AI-based system is predicting or working or controlling, potentially controlling, that is giving the control inputs vis-a-vis what the actual thing is going on. And then after a few months only, one would take the decision whether the AI system is behaving better and replace the existing system by the better one. So these are the ways in which one actually goes about implementing AI-based systems. So, well, there's not much point in my reading through these. So anyway, let me leave this out. So this is about the first part. So in fact, I went through it faster than I thought probably. I thought I'll take half an hour, I finish in 20 minutes. Are there any questions about these, or am I allowed to ask the audience for any questions about these at this point in time?
Sir, half of the...
Hello?
Yes, sir. Am I audible to you, sir?
Yes, but there's no slight echo, but that's all right.
Yeah, sir. Actually, the half of the audience are in live, so you can drop a question. So meanwhile, let's wait that whether audience are able to answer for
Okay.
the same one.
Okay, so my remarks here is that I have finished the first part, which is the generalities of application of
So yet
machine.
we don't have any question.
Okay, so I'll move on
Yeah.
to my
Yeah.
main.
Right, sir. Yeah.
Okay. So here I'm going to talk about adaptive critic design for extreme learning machines applied to drifting in industrial processes. So let's not be, too much kind of floored by the kind of words that are used, adaptive critic and extreme learning machine and all that. So I'll gradually explain all these things as we go along. Okay. So you see what happens is that when you, let's say there is, let me see, this is a kind of cyclical diagram. So the starting point could be just what are called as continuous time systems. So continuous time systems, most systems in the world are any kind of dynamical system, unless it is event based, it can be looked upon as a continuous time systems. Mostly when we deal with actual solutions, we discretize these continuous time systems and look at the solutions. Okay. So what do we mean by adverse digressions? So when we have continuous time systems or dynamical systems, sometimes they tend to behave differently and it brings down their, the level of performance. So in fact, I'll explain this in more details down the line. So the thing is that in continuous time systems, which are a kind of ubiquitous across most things in the world, there can be adverse digressions, and then there are ways of taking care of these adverse digressions, and one of them use machine learning techniques. So I would say the most important or the easiest or the most natural of them is to use machine learning techniques. So we are going to talk about an instantiation of this in manufacturing industry. And we will talk about machine learning techniques for advanced prediction. And we'll first talk about artificial neural networks. Then we'll go on to something called as adaptive critic techniques on artificial neural networks. So, like I'm just trying to say what is the outline of my talk here. Okay. So of course, you may not be fully familiar with what is continuous time systems, what are artificial neural networks. I'm assuming that you know what it is broadly, because I think you already have some background. Adaptive critic techniques, I think most of you will not be aware of. Then extreme learning machines you'll not be aware of. So we'll first talk about adaptive critic techniques on artificial neural networks. Then we'll get into machine learning techniques for advanced prediction using ELMs, extreme learning machines. And then we will actually use adaptive critic techniques on ELMs. Now, when this work was done, it was done for the very first time because adaptive critic techniques did not exist in ELMs. So we also have filed patents, and we have got a number of papers around this as well. So let me now get into more understandable things. So a very large class of physical systems that are natural or man-made, as well as systems in finance and economics, can be classified as continuous time in the sense that their parameters of state are continually evolving with time, unlike, say, finite state machines. I hope you understand what are state parameters. I think, basically whenever you have any dynamical system, there'll be a lot of variables associated with this. And if you look at the variables at any snapshot in time, they tell you the state or the condition of the particular process at that point in time. And that is why these are called as parameters of state. So this includes biological, meteorological, geophysical systems, as well as industrial processes, vehicles, machinery, distribution networks, stock markets, national economies. All of these systems have one common characteristic, Namely, they are susceptible to occasional but rapid adverse digressions in performance. The word rapid being relative to the time scales of the respective process. So for example, when you talk about, let us say, if industrial process in steel manufacturing is something called as blast furnace. Okay, so we'll have a look at that in one of the slides. So in a blast furnace, the time scales are of the order of maybe of the order of hours, or maybe of the order of 45 minutes or so. Okay. On the other hand, we have got, say, grids, say electrical distribution grids. Okay. And there your time scales are of the order of, I would say, milliseconds, right? So when we say that all of these systems have one common characteristic, namely they're susceptible to occasional but rapid adverse digressions in performance, the word rapid being relative to the time scales of the respective process. So a blast furnace may get into a different state in a matter of many hours, whereas an electrical distribution grid or network can go down in just a few seconds. It is clearly very desirable that the rapid adverse digressions in such systems be detected before they have initiated, so that timely corrective action can be taken to prevent the digression or avoid or minimize its impact. So I think these are all understandable, whatever we have talked about here. Now, the state of a continuous time system can be described by a large number of parameters. And just now we said that these are parameters of state. Some among the multitude of parameters acquire, now this is very important. I think this is a bit abstract for us to think about it. Some among the multitude of parameters acquire a specific combinatorial relationship before the incipience or the start of a specific type of adverse digression, that is a fault. It is the acquisition of this relationship by a subset of all the parameters that engenders or creates the digression. I hope the part that is written in italics is understandable. Unfortunately, as I said in a class, we keep getting feedback and I can see the faces. This is one of the major issues in online discussions. We cannot see the faces of the students. Of course, here it is not just students, it's the audience. So this is a very important thing. Let me just repeat it for the sake of its importance, that whenever we have an adverse digression like a fault coming up, it is sum of the state variables that acquire some specific combinatorial relationship that creates a specific type of fault. Okay. Thus, it may be stated that there is a one-to-one mapping between the formation of this kind of relationship and the consequent digression. If the formation can be captured, now this is again very important. If the formation can be captured in real time of the process, mind it. If the formation can be captured in real time, then the digression can be predicted in advance with consequent advantages. When data of system state parameters is available in real time, then machine learning techniques can be used to predict the acquisition of this relationship. In this talk, we discuss the development of such a machine learning technique using ANNs for a specific process, and that specific process is the continuous casting sub-process in the steel manufacturing process chain. From ANNs, artificial neural networks, we move on to something called as extreme learning machines, which is actually a cousin sister of ANNs, you can say, and also discuss the disruptive effects of industrial drift. We will talk about industrial drift down the line. We discuss how adaptive critic techniques can be used to neutralize the impact of process drift, and then explain our pioneering development of adaptive critic techniques for extreme learning machines. Okay, so we get into the steel manufacturing process chain, and here we have, if you go from left to right, of course, by looking at the arrows, you can make out the direction of the process flow. So we start with, here we are talking about the basic minerals, so iron ore, and then we have got coal. And essentially what happens in the core part of a steel manufacturing process is that the oxygen part of iron ore is stripped off from the iron using some kind of reduction techniques, which could be based on coal. Most of the plants today are based on coal. However, it could also be based on other reduction agents like hydrogen, for example. And that is what is supposed to be called as clean steel, and gradually it is getting more and more popular down the line, but still makes a very small percentage of net steel production. Okay, so then from here we move on to different kinds. So what you see here is a blast furnace. We'll not get into the description of this. Now, steel is a 100% recyclable material. So on the one hand, while you can actually pull out the iron and corresponding steel from the earth, from the minerals, you also have a lot of existing stuff like, for example, cars or other kinds of steel materials like construction material and so on and so forth, which also go into as scrap And then from the scrap, it is actually called as recycled steel. And that is also one of the inputs into the production of steel. Okay. Then there are different stages. So, like when you have to keep in mind that whatever is coming out of the blast furnace is in liquid form. It is liquid iron because it is mixed up with many impurities. And then there are some processing stage, all at the liquid level of the steel or of the iron, you can say. Where number one, you kind of remove as many impurities or as much of the impurities as possible. And number two, based on the customer preferences, you alloy or create new properties in the steel by alloying with different metals. Okay, so all of this is done at the liquid stage. Then from the liquid stage, now you transit to the solid state, and that is done through something called as continuous casting. In my next slide, I'll just blow up this part of the continuous casting. The output of continuous casting is either slabs, or you can say for flat products like, for example, car bodies or white goods. And you can have blooms or billets, which are basically going into the construction industry. So the former are called as flat product, and the latter are called as long products. Okay. Now, after this, there are rolling stages and then annealing stages and all that, which is not contained in this particular slide because my idea was to focus on what is continuous casting. Okay. So here we get a bigger view of continuous casting and also tell about the phenomena of breakouts that happen in continuous casting, or that potentially can happen in continuous casting. Okay. So here we have, this is just a picture, but let's look at the schematic diagram. So you have liquid steel coming in huge buckets. So here you have a view of the bucket, in which the steel is coming. This is called a ladle. Actually, you don't see a human next to it, so you cannot make out what is the size. So generally, a ladle is of maybe a diameter of about 2.5 meters and a height of about 4 meters. So you can make out how huge it is. Okay. So then the core part of, okay, so from the ladle, now ladle actually brings this liquid steel and drops it into a kind of a buffer, which has got some jargon called as tundish. Okay, so it is put into this tundish, and then from here it is actually sent into the what is called as the cooling mold. Now this cooling mold actually converts is a core part which converts the liquid into the solid. All right, and when it converts into the solid, it also takes on the shape of the mold. So if you look at a mold from above, it looks like this, broad shape, so it's a rectangular shape, and then there's a certain depth. So one continuous casting mold, you can say, would be of the order of, say, 1.5 meters wide. Now I'm talking of very general, there's a lot of variations, okay? So maybe of the order of 200 millimeters thick and of the order of 1 meter in depth, all right? So this is the depth direction where what is shown here as Z, this is of the order of 1 meter. And then you have the yellow part is the pure liquid part, okay? So from the tundish, now this is the tundish. So this is the ladle, tundish, and then here you have the tundish dropping, or the steel flowing from the liquid steel flowing from the tundish into the continuous casting mold, and then it comes in through a pipe which is called a submerged entry nozzle, SEN. And then what you see here is the expanding boundary of the red zone. This is actually the shell that is getting formed. So now let us understand what happens in the continuous casting mold. So in the continuous casting mold, actually this gives a bigger view of that actually. So without getting into too much of details, broadly you can say that the steel like the mold walls are made of copper. Of course, it has to be held by a steel jacket outside, but let's say the walls are made of copper with a strong, with a strong outlay of pipes carrying water from bottom to the top, and this water is what removes the heat from inside through the copper plate into the water, and the water takes the heat out. Okay, so what happens is that the steel that is liquid, now you can say that around 1400 1500 temperature would be the, let's say, the temperature of melting, the melting temperature of steel, that is called as, anyway, let's leave out all those technical terms. So the point is that once the steel comes very close to the copper plate, it starts losing heat, and the heat goes out, and as a consequence the temperature falls. It falls below the temperature of melting, so it forms a small thin shell, and as it goes further down, the shell expands. Okay, now just one fine detail: the steel, the molten steel itself does not touch the copper plate. Instead, there's a thin lubricating film which stands between the copper plate and the liquid steel, and it is this thin film through which the heat passes from the liquid to the copper plate. Okay, now this gives a view of what really happens around the region where the solidification is taking place. So what you have in this, as I said, the outer part is the copper plates of the mold. Then inside, what you see dot dot in white is the pure liquid. What you see here, the red, is actually a kind of it is actually, sorry, it is a mushy zone, in the sense that it is a shell, but it's a soft shell because it has just been formed. All right, and between the shell and the copper plate, there is this pink region, which is actually the lubricating film. Now this has been kind of blown out of proportion a little bit because it is thinner than what is shown here. Okay, what you have in the now, this lubricating film is not uniform. It is very difficult to keep it uniform all throughout, and a good deal of research and experimentation and technical improvement has gone into how to keep this lubricating film as uniform as possible. So you see formation of this, what you call as air bubbles inside. All right, whenever you have an air bubble, it restricts the flow of the heat outwards from the liquid to the copper. Okay, as a consequence, the shell formation there is not proper. Conversely, wherever the lubricating film is very thin, it might just happen that the shell that is getting formed at the very beginning towards the top, when it is very soft, it touches the copper and then it starts sticking to it. Okay, and when it starts sticking to it, what happens is that you can understand that the entire thing, the steel, including the solidified shell, is gradually going down. As it is going down, if some parts tends to stick, but the other parts still continue to go down, then it creates a strain and it tears. And as soon as it tears, what really happens is that the entire liquid steel that is above this, that means suppose it is starting to tear here, practically all the steel that is there right up to the tundish will flow out. Okay, and when it flows out, where does it flow out on? Now this brings me to the second part of what happens outside the mold, and then I'll come back to this. So when the steel extracts or comes out of the cooling mold, it is supposed to be having a uniform shell all around, which is now formed, which is now kind of solid. It has strengthened by the time it comes out, not the soft one that was at the very beginning. And it is sufficiently strong to be able to stand the liquid pressure all the way to the top. All right, it comes out, but then inside it is still liquid. So there, because this was vertical, it has to be, it's now turned around and made it to vertical. It passes over rollers. These rollers themselves are cooled, and there's a cooling spray also on this shell here. I mean, on this, you can say, actually this is called a strand, which is going down. So this gradually cools, and then the outer thin shell gradually thickens, till finally the liquid is completely gone and it is entirely become pure solid. Okay. So what happens is that when you have a breakout, the liquid flows out, it flows onto all these rollers. Okay, it flows and it completely chokes the process. So, and it holds up this entire process for many hours. All right. And now you can understand what is happening, that from the blast furnace or from the, you can say, the steel making shop, you have got liquid steel coming, but then you do not have the continuous casting line operating, and you cannot hold the liquid steel in the ladle for indefinitely long periods of time. All right. On the other hand, if it is a continuous process down through the what you call as the rolling parts also, then they will also be deprived of the steel that is supposed to be coming from above. So breakout is a major undesirable event, and one has to find out ways and means of preventing a breakout by predicting the formation of a breakout as soon as it has happened, or if possible even earlier. Okay, so this is just giving a photographic. So this is a view of what I was talking about just now, the liquid coming out. This is of course a schematic diagram, and then it turns around and then it becomes completely solid. And then when it is solid, it is the continuous part is now cut into discrete slabs, and so on and so forth. Here it shows the vertical view of a particular continuous casting machine after a breakout has happened. So you see these rollers. Now between the rollers, you have a small region through which the strand would have passed, but then the strand is not there. Instead, the shining silvery part that you have is actually the liquid steel that has flown out, and then has again cooled on the rollers and has completely blocked the process. And it takes many hours to restart the process again. Okay, so obviously, now coming to the next point, obviously one would like to somehow prevent breakouts from happening, right? So how does one prevent breakouts from happening? So for that, I have actually, the slides, I have not got all these details, but then one can always talk for a few hours on this as well. But the whole thing is that there are breakout prevention systems. And actually, I was working for many years in Tata Steel. Me and my team, we developed something called as breakout prevention system. We call it as breakout detection system, or BDS, and we have implemented it. And I would like to say that the system that we implemented in Tata Steel had saved hundreds of crores per year for the company for more than 15 years. And it is running now, but with many modifications. Okay. Now here I'm going to talk about something which is not the breakout detection system that we had spoken about, I spoke about just now. It is, see, breakout detection system by its very nature, it actually looks at sensors which are thermocouples. I've not shown them here. Okay. And it, by looking at the thermocouple signatures, one can make out that a sticker or a tear has just taken place and what action has to be taken to prevent the sticker from growing and the break from healing again. All right. The question is that this happens, or this prediction occurs after the breakout or after the break has already happened, after the tear has already happened. The question then is, can we predict in advance that a tear is going to occur? Now you can understand the risk element of this. One is that we are predicting in advance. Suppose this was the only system and it kind of substitute for the existing system that is based on responses after the event has happened, but maybe a few milliseconds after the event has happened. The question is that here we are trying to predict or preempt the occurrence, say that it is going to happen, take action to prevent it from happening. All right. Now, you know, whenever you take this kind of action in any kind of application of machine learning in manufacturing or any kind of industry, you usually say that something is going to happen or not going to happen, and both are risky. So if I say too many times that a fault has been generated and a breakout about to happen, okay, then every time I'll be taking corrective action, which is going to disrupt the stability of the process, which is not desirable because it affects number of things. Number one, the throughput. Number two, the quality, and number of other things. On the other hand, if I say that, okay, if I am trying to be more liberal and say, okay, let me not unnecessarily say that something is going to happen, but then I say that there is no breakout going to happen, the breakout actually occurs. Now that is an even more drastic loss for the system. So one has to fine tune the system so that, you know, like we have the accuracy of the system is as high as possible. So, you know, in machine learning, there are things known as accuracy. Then there's something called as F1 score. There's something called as precision. There's something called as recall. We'll not get into all of those things now. Okay. So let's just look at it in a different way. So we have now, I've actually skipped many other things that have been done in between, and they have been actually published elsewhere. I'm just going to come to the end of those level of calculations. And we are saying that we have developed an ANN which predicts breakouts in advance. All right. And then what we are trying to do is, first we are trying to not get into the breakout aspect of it. We are just trying to say that before a breakout is likely to occur, we are trying to predict that, we are just trying to predict the divergence of a system. So let's try to understand what we are talking about. We say that there's a continuous casting process running, and if the process is absolutely normal, this ANN is going to give an output of 0. Okay. On the other hand, if the process is absolutely, I mean, you can say there's a process upset, like a breakout has actually going to take place, then we say the output is going to be 1. But the ANN does not always give either 0 or 1. It gives a whole range of values all the way between 0 and 1, right? So what do? We set 0.5 as the intermediate, and we say that if the prediction from the ANN is the output from the ANN is below 0.5, between 0 and 0.5, we say that the system is normal. When we say that the output is between 0.5 and 1, then what we are saying is that a breakout is likely to occur, a breakout is about to occur, so preventive action has to be taken, right? Not that breakout has actually occurred. All right. So the thing is that we have got literally hundreds of cases where we have actually taken we are basically taken, you can say, screenshots or snapshots in time, taken the inputs, generated the outputs, and then compared with the actual situation. All right. So here what we are predicting is, say this is a large number of values. So what is important is the y-axis. So y-axis, we have values from -1 to +1. Now what are these? So it says that we say that the actual value, suppose it is 0 and the predicted value is 0.3. All right. So we take a difference between the actual value and the predicted value. In this case, it's going to be -0.3. All right. Okay. Now let's suppose that once again, the actual value is 0, but the predicted value is 0.7. All right. Then the actual value is, then the difference between them is -0.7. All right. So we can say that if any value comes which is less than -0. Which is between 0 and -0.5, then it is correct, it is not wrong, but anything that is beyond minus 0.5 is wrong. Now let's look at the other side. If the actual value is 1 and I am predicting between 0.5 and 1, then the difference is between 0 and 0.5. Okay. On the other hand, if the actual value is 1 and I am predicting 0.3, then the actual value is 0.7. So I can say that in the range of minus 0.5 to 0.5, if I get my difference between the actual value and the predicted value and the actual value, I say that I am making a correct classification. On the other hand, if I'm outside minus 0.5 or 0.5, this band, it is a misclassification. I hope this part is clear. Misclassifications in training data. Now, again, I think you understand also that in any machine learning, we have training data and we have testing data. Okay. So what is training data? So we have the total data and we split it up approximately 80-20 into the part which is going for training of my model, basically my model parameters, and the balance 20% where I test that whatever parameters I've created so far, how good are those parameters? Is there a need for further training or there's no need for further training as of now? So misclassifications in training data is normal cases is about 2%, breakout cases is about 6.3%. Okay, and standard deviation around zero line is 0.2. Now this is from the ANN that we talked about. Now please understand, any industrial process is noisy, and a complex process like continuous casting is extremely noisy process. What do you mean by noisy process? That there's a lot of fluctuation in the sensory inputs. Okay, so some of the inputs are sensory inputs, some of the inputs are kind of inputs derived from input parameters, but then passing through many empirical relations. So anyway, this is an extremely noisy process. Hence, novel techniques have been developed and implemented to annul the impact of noise. So we'll not get into that. Okay, so I have actually missed out some misclassifications in training data, misclassifications in testing data. Now, whenever we move from training to testing, we would expect that there will be a deterioration in the accuracy levels. So normal in training case was 2%. Here it is testing data, it is 4.3%, and breakout cases it is 18%. Standard deviation has become worse. Okay. Then we go to see what we are actually trying to do. This is what I'm trying to show you here. So now this is a continuous, see what we have on the x-axis is time. Okay. What we have on the y-axis, now there are three different curves being plotted. I'll not get into detailed description, just tell you about it. One is the moving average, is it average? I think moving abnormality index. So abnormality index is the value, as I said, goes to 0 when it is absolutely normal, goes to 1 when it is absolutely wrong, otherwise it stays in between. All right. So that is abnormality index. What is NICC? Now let's not get too much into that. It's basically some kind of an index of continuous, normality index of continuous casting. The deep red line is the alarm. So the alarm is actually generated using some kind of a relationship between NICC and MAI. All right. So you see that in the continuous process, now these are actually 3600 is 1 hour. Okay. So it has gone for about 6-7 hours, 7, 8, 9 hours almost. And it has been continuously behaving well. But then towards the end, there is a deterioration in the entire process and there's a breakout about to happen. And this, our system is alarmed with this value, which is coming to 1. So alarm is either 0 or 1. Okay. So we have raised an alarm before a breakout is going to occur. Now, the next is that, see, please understand that this is not data from Tata Steel where I had worked. Okay. So let me not get into from where it has been taken. Now, the thing is that, as I said, there is a very fine-tuned prediction because you should not over-predict the alarms. You should not under-predict the alarms. The cost of under-prediction is much worse than the cost of over-prediction, but then the over-prediction can happen large number of times. So overall, neither over-prediction nor under-prediction is desirable. So here we have shown that we have never predicted alarms even once before and predicted it only once just before a breakout has actually happened. Okay. Now remember, this was running in parallel, like this is what I talked about earlier. So we were not really controlling the system. If we were controlling the system, the breakout would not have happened. Okay. Now here we are showing a different, another sequence actually. You see what I showed you, those 8 hours or so, this is one sequence of casting. All right. After a sequence of casting, what has happened is that it is temporarily paused, the condition is changed. So one again starts a new casting sequence. So in this casting sequence, you find there are a lot of variations in the abnormality index. NICC has also been changed, been fluctuating, but our system has never given an alarm unnecessarily, even in spite of all these fluctuations. Another thing that you notice here is casting speed, but then that's not important. So our system was working quite well and giving, I mean, fine-tuned from both the aspects. Now comes the next issue, industrial drift and its impact on machine learning based analytics. So, sorry. So when I started, I had mentioned that continuous systems drift. Particularly industrial systems drift very much. Okay, now what do we really mean by the drift? So drift basically means that if I give almost the same inputs as I had given, say, maybe 1 month back, by inputs here we're talking of actual material, raw material inputs or processed raw material inputs. Okay. So when we give the same inputs, we get different kinds of output, and the machinery or the process it does not process the inputs in exactly the same way. That is what we call as process drift. All industrial systems drift due to the following reasons. One is the wear of machinery. Two, of course, is changes in input materials. And three is that, if you actually see a manufacturing system, you always have operations personnel, and the personnel are continuously trying to improve the system. All right. So operations, experimentation, and continuous search of improvements. So these three things together make an industrial system drift. Now the question is, what really happens in machine learning? The corollary of this drift is that machine learning models trained to recognize combinatorial relationships among parameters based on past process data lose their accuracy into the future. Now, what really happens in machine learning? I think most of you will be familiar with basic machine learning models. So you have, you pick up when you here let's say talking mainly of supervised learning. So you have a process. The process has got some inputs and some outputs, right? So if I take a particular time instant, I've got let's say 15 inputs and one output. All right. And then in this way I pick up, so this is one sample, say 15 plus 1 variables. In this way I can pick up thousands of samples over time, over a process of maybe months. All right. And then I use these samples to train a machine learning model, which learns the functionality of the output to the inputs, right? And when you say it learns the functionality of the outputs to the inputs, what does it mean? It maps the functionality of the outputs to the inputs as embedded in the data that has been picked up onto the coefficients or the weights that constitute that model. Okay, so you can say the coefficients of the model, or in terms of artificial neural networks, we talk of the weights as the coefficients. Okay. So what happens is that when a machine learning model learns, these weights or coefficients are a function of the data it has been trained on, right? What is the data that has been trained on? The data that has been trained on a certain functionality. Now, when the industrial system drifts, basically what we are saying is that the functionality of the outputs to the inputs are also drifting. All right. So that means the data on which I have trained it, maybe over a period of the past few months, and which embeds the functionality that has been picked up from the process, will no longer, as my system drifts, that functionality does not anymore represent the true functionality of the process, because that functionality has drifted. Okay. So as a consequence, let me repeat this. The corollary of this drift is that machine learning models trained to recognize combinatorial relationships among input parameters based on past process data lose their accuracy into the future. I hope this is clear. I don't have a means of feedback. Okay. To neutralize the effect of drift, machine learning models have to adapt to these evolving relationships between parameters. Now, this is a very important statement. Okay. So either I take out my machine learning models and retrain it and then put it back in place, or in the process of running online, I adapt my machine learning models to modulate the relationship that exists between the parameters. So if it's an ANN, it means that in some way I modulate the weights of the ANN to account for, or to take into account, or as a function of the drift that is taking place. So how do we do it? So adaptive critic techniques founded on reinforcement learning are a class of techniques used to adapt ANNs controlling real-time systems. Okay, now we get into a little bit of mathematics, and I think some of you will start having a little bit of difficulty in understanding this. Also, I think I have to move a little faster now. Sorry. So the basic idea of adaptive critic systems is to modulate the control parameters so as to minimize the quantity ut, which is called the utility function, defined as. Now this ut, so don't get overwhelmed by any of these numbers. You just see there's a fundament. I mean, forget about the half part. There's a xt minus x target t. Okay, so this is a vector because x is made up of a number of parameters. All right. So we have xt minus x target t, and this is basically, you can look upon Q as an identity matrix for a moment. Okay. So you have xt minus x target t squared. All right. Plus half of rho of ut transpose. Now, what is ut? Ut is actually the amount of control effort that is needed. So this capital ut reflects that how much is the deviation between the actual states created versus the targeted states, and how much of control effort goes into attaining that closeness or that distance. All right. Now, those who have seen machine learning models and trained machine learning models and are aware of what is regularization would see an uncanny similarity between the error term, the mean square error term that we see in, say, supervised learning processes when we impose a regularization, either L1 or L2 regularization on that. Okay, rho is just you can say a constant, some kind of a coefficient of regularization. X and X target are the running and targeted states. U represents the control parameters, and rho a regularization term. The minimization has to be done for all time into the future. Now, what I was trying to say is that basic idea of adaptive critics is to modulate the control parameters ut so as to keep the quantity capital ut, called the utility function, to a minimum, right? Now that means the ut has to be a minimum not only now at this current t, but has to be minimum for all t into the future. So this minimization has to be done for all time into the future. Hence the term jt, called the cost to go function, is defined by the Hamilton-Jacobi-Bellman equation and is written as jt is equal to summation from k is equal to 0 to k is equal to infinity gamma to the power of t ut plus k. Okay, so this gamma is actually, like what is, it is between 0 and 1, and I'm forgetting that there's a jargon for this. It's a very simple term actually. It is actually saying that when k is equal to 0, then the impact is maximum, and then when as k gets into the future, so remember k is less than 1. All right, so as k increases, the impact of this term gamma becomes less and less and less. So although it is written summation is k is equal to 0 to infinity, it will actually be k into some number of finite terms, because beyond those finite terms, this gamma is effectively 0, so this term drops off. I mean, there's no more summation. So forget, and this is just a bell for a period in my university where I'm sitting. So this can also be written, I can write this as jt is equal to ut plus gamma t plus 1, I mean gamma jt plus 1, and so on and so forth. Just trying to get the name of that gamma, but is anyway, whatever it is. So classical adaptive critic philosophy is to juxtapose two consecutive time step values of jt. So we don't really know what is jt, and it depends on the value of gamma that you have put. But there also you can depend on that I'll consider some terms and not consider some terms. But the classical adaptive critic philosophy is to juxtapose two consecutive time step values of jt, evaluated using a set of three ANNs, control ANN, critic ANN, and the identification ANN, to create an error function for simultaneously updating critic and control ANNs. So, I think I'll not stress too much on the maths part. Essentially, the idea is that we try to juxtapose between the jt at the current t and the jt plus 1 at the next t, all right? And the difference between them, see, if this is correct, then jt minus these two terms at the right should be exactly equal to 0. But then if the jt is, or if my ut is not all the time near 0, what is going to happen is that e1 is going to be some quantity which I want to minimize. All right. So for that, now the thing is that I don't know what is jt plus 1, right? So what do I do? So for that, actually, we have got something called as control ANNs. Then there's something called as critic ANNs, and there's something called as identity ANNs. So as I said, it's a set of three ANNs. Now, again, don't get perplexed by this figure too much. If I can just divide this into two parts, one is that what I have at time t, and one is what I have at t plus 1. Okay. So this ACANN is the action ANN, that which takes the control action. Critic ANN is that which tries to judge, looking at the value of J and looking at the value of E, whether action ANN needs to be revised or updated or adapted or is perfectly fine. And identity ANN just merely takes the state inputs, the control inputs, and predicts the next state. Okay, so so what we have here is action ANN, which takes xt, x target at, now this T stands for time, xt, x target T, this T stands for target, is not transpose. Okay, and ut minus 1 is the input that had come at the previous time instant, and this action ANN generates ut, that the control action at the current ANN, and then the control action plus the target values will both, I mean not the target values, the actual states pass through the identity ANN and predicts the xt plus 1. And then this xt plus 1 is used to generate the same kind of setup as I had done at t plus 1. So I have ut now xt plus 1 and xt t plus 1. Now ut comes from here, from what is the prediction here. xt plus 1 comes from the prediction of the identity ANN, and then this gives rise to ut plus 1. Now in the critic ANN, what happens is I get the inputs ut, xt, and xt desired xt, and it gives rise to jt, and this gives rise to jt plus 1, and then jt plus 1, or rather jt minus ut minus jt plus 1 gives rise to e1, and this e1 is like a error term which is used for again retraining the action ANN. So action ANN, on the one hand it controls, on the other hand concurrently it is also being upgraded by the control ANN, by the critic ANN. Critic ANN does not do the actual control. Actual control is done only by the action ANN. Critic ANN is the master which controls the action ANN. Okay, now here the identification ANN in the classical architecture is needed to simulate values at the next time step and is a source of inaccuracy. Now the actual requirement is for two values of JT at two consecutive time steps. And in real-time systems, one can use the real values from the previous and current time steps, making IDNN redundant. This entails changes in the formulation and architecture with the error term now modified too. So I have actually, I mean, this is something that we have done, and we have also applied for a patent. So E2 is actually written as, now this is the second kind of error. Instead of using JT plus 1 and JT, it uses JT and JT minus 1 and UT minus 1. Okay. And then using this, if I use this, then I can make the identity ANN redundant, and my new architecture becomes, now I've got only two levels. I don't have any IDNN. I've got action ANN, critic ANN, and here also I got action ANN and critic ANN. Okay, so in this case, this is what has happened at t minus 1. So I know what was the target at t minus 1. I know what action was taken at t minus 2. I know what states went in at xt minus 1, and I have ut minus 1. Okay, and then at the current time step, I have x transpose, x target, ut minus 1, xt, and giving rise to the ut. Okay, so the difference between, so this now gives rise to jt, the critic ANN, and this gives rise to jt minus 1, and between them I have got e2. So okay, now this is the last bit of very conceptual thing. Please try to understand this. When we were trying to look at ut earlier in the classical case, I had said that ut is a control problem, right? It is used as a controller, and then it is looked upon as xt minus x target t, and then we add a ut over there. Here, in our case, where we are trying to predict, we're not trying to control the system per se. We are trying to, we're not trying to develop a model to control the system. In place of that, we are trying to develop a model to monitor the system. Now, what do you mean by a model to monitor the system? So this model takes in the system parameters and gives an output of 0 if the system is absolutely normal, gives an output of 1 if the system has completely degraded, and anywhere between 0 to 1 is like giving the condition of the system. All right. So if let's say the model predicts 0.2 or 0.3, means the system is nearly normal. If it is predicting 0.7 or 0.8, that means system is digressing, and you have to take some action to set it back to proper behavior. So in this case, the definition of ut is not the x target t, xt minus x target t. It is actually expressed as something like vt squared. Now again, as I said, q is the mathematical formalism. Assume that it's an identity matrix. So we have got vt squared. So ut is actually vt squared, where small vt is what? Now small vt is basically a function which looks at whatever is the prediction from the UT, that is my UT is the value which is the prediction of the condition of the system. So as I said, UT is equal to 0 means very good, UT is equal to 1 means very bad. Mostly it is between 0.2 to 0.8. Okay. Now VT maps, what VT has to do is, it has to tell that how good or how bad at a given point in time is my UT versus what is the actual state of the system. So the actual state of the system depends on the process parameters. So then VT is actually some function of the juxtaposition of the UT, that is the prediction, versus the process parameters. All right. Now the question is that, by how can I predict, by looking at the process parameters, the system is good or system is bad? So to do that, I actually have to, one needs very keen domain understanding. One has to be a domain expert to be able to say, by looking at the process parameters, the system is healthy or system is unhealthy, right? And then if it so happens that UT is giving very small values, but process parameters are telling that this process has degraded significantly, then that means my F should be able to convert it into a large value of VT, which means that my UT or my prediction parameter of the how good my model is telling me that my model is very bad. Okay. On the other hand, if process parameters are telling the system is very good and UT is small, then my VT is also going to be small, which means that my utility function is also very small, telling that my monitor, or you can say my monitorer, if you want to call it that way, my model for monitoring the system is a very good model at this point in time. So VT is such that if the monitored process is healthy, VT is small and hence UT is small. I hope this is understandable. Okay. In fact, let's look at the other extreme, that UT is giving very high value, means telling the system is about to degrade significantly, but my process parameters are coming out to be such that it appears that the process is very good. So whenever there's a divergence between the values of UT and the actual state given or exemplified by the process parameters, my F and corresponding VT is going to be a large value. My UT is also going to be very large. Okay. UT, the utility function, tells how good is my monitoring. To just repeat, just as UT in the control case would be manifesting how well my system is controlled, here UT manifests how well the system is monitored. Okay, so these are all very critical. See that no one is going to tell you. Only people who are experts in the particular domain can generate values like VT and corresponding UT. Okay, so the validation approach is to allow the, okay, now what we are trying to do is, we are using an ANN to predict the value of small UT and then convert it into the large UT, okay, the utility function. And then by the utility function is further mapped into the value of JT using that architecture that I showed you. And then using the values of JT, juxtaposing JT with JT minus 1, I'm going to get an error function which is going to retrain my in this case, although I still call it as control ANN, actually it's better to call it as a monitoring ANN. Okay. So the question is that if I have a monitoring ANN and I have a critic system also, and then now let's look at what I'm talking about here. The validation approach is to allow the process to run for weeks and run concurrently both the adapted by the mechanism we just now discussed and the non-adapted, that is U left free. The action ANN is no longer being controlled. Okay. So the adapted and the non-adapted predictions. The UT from the prediction under adaptation should stay lower than the UT of the prediction without adaptation. So here, x-axis represents hours, but these are not continuous in calendar time. So, like although I'm showing for 81 hours, please keep in mind, like we saw the figures earlier, that we have a sequence, and the sequence was of the order of anywhere between 8 hours to 10 hours. Could be more, okay. So the thing is that we are just leaving out the times in between and concatenating the times of the actual running of the process and then creating this plot. And here you see that the red is the U from non-adaptation and blue is the U from adaptation. And U from adaptation is definitely staying lower than the U from non-adaptation. Okay. All right. While validation results are good, now here we come to another turn in our whole thing. I think I'll go on for about another 10 minutes and stop for questions. Because I have a feeling that the drift between your understanding and my talking is becoming more and more. So while validation results are good, the adaptive critic process requires repeated retraining and creates heavy loads on the processing platforms. And this brings us to something called as extreme learning machines. Now, I'm not going to get into the details of extreme learning machines. I'll only say that there are two major differences. Extreme learning machines are very similar to artificial neural networks, or you can say multi-layer perceptrons. If you are aware, I think you should be aware to that extent. So in this case, extreme learning machine is like a multi-layer perceptron with 3 layers, one hidden layer, and of course one input layer and one output layer. That is what you see here. Okay. There are two major differences between a typical feed-forward ANN with 3 layers and ELM. One of them is that the first matrix, so when I have 3 layers, I'll have 2 matrices. The first matrix between the input layer and the hidden layer, and another matrix between the hidden layer and the output layer. So this first matrix is actually not trained. It is taken randomly. It is selected randomly. Now, so ELM is architected like multi-layer perceptrons with 3 hidden layers and non-linear activation functions. The elements of the first weight matrix, the Ws, are selected just arbitrarily, randomly with some constraints. Now, please keep in mind that although we say randomly, there is also a lot of consideration for the randomness. Okay, so one can have one can have absolutely flat random, we can have a Gaussian random, we can have different kinds of standard deviation in the Gaussian random, and so on and so forth. The weights of the second matrix, the weights of second matrix are the betas. You can just call them as weights only, are then solved for as a function of the previous layer weights and is obviously training data itself. So what is solved for in the ELM is just the weights, the second layer weights, which will, like any ANN, it will be a function of the input, the training data. In this case, it will also be a function of the, apart from the training data, it will also be a function of the values that we have considered for the first layer weights. Okay. And so this is the first major difference between the ELM and a 3-layered feed-forward artificial neural network. One is that the first layer weights are decided randomly, and 2 is that unlike ANN, which is trained using backpropagation or some kind of a iterative scheme, in the ELM, we just look at the difference between the outputs and the desired outputs, and we force the outputs to be equal to desired outputs, which actually converts it into a single shot matrix inversion problem. And we solve this using Moore-Penrose inverse. Okay. So because it is not an iterative scheme, it is solved using a single shot matrix inversion. So actually it takes about 2 orders of magnitude time less than an ANN and generates almost the same level of accuracy. Okay. So I'll not get further into this aspects because then this itself will take me about close to 1 hour to explain. So now what we did was we compared the ELM. So it's the same kind of comparisons you had seen earlier. We compared the ELM and an ANN, and we looked at the levels of accuracy. So I'll just try to show you here. ELM with L is actually the number of nodes in the hidden layer. Okay. And we have so this is ELM with L is equal to 182 and 2 hidden layer feed forward neural network. So we have prediction data, test training, classification error, normal cases, plus classification error for breakout cases. So we see that when we looked at normal cases, then let's say that training error is say 2.06% for ANN, and it was 3.79% for ELM. And then when we went to breakout error, we saw ELM had an error of 5.4%, whereas this had an error of about 18%. And for the training error, this was 4.14%, this is 6.29%. So generally, you can say ELMs generate about the same level of accuracies as feed-forward ANNs. Important, comparable levels of accuracy have been obtained on noisy industrial data with training time reduced by 2 orders of magnitude. This brings us to adaptive predict systems for ELMs. So I said that one of the major issues with adaptive predict systems where ANNs are used is that it takes a lot of time for the training, time and effort for the training or the retraining or the adaptive training part. Instead, if I use an ELM, I can get about the same level of accuracy, but then I have a technical challenge in developing an adaptive predict system for ELMs. So how we obviated that that challenge. So why is it so difficult and unattainable as yet? At the heart of the problem lies the very mechanism that gave ELM its stated advantage, direct solution by forcing output to match with desired outputs. The adaptive predict process, as seen in ANNs, cyclically updates the predict NN and then the action ANN. And this is enabled by the fact that the error between the cost to go functions J at consecutive time steps is iteratively fed back into the weights of these ANNs. How can a critic ELM and an action ELM be cyclically error mitigated in a direct solution framework? To attain this, a new architecture and concomitant mathematical framework was created, which is explained next. Now you see I've got just 15 minutes left, and I would probably prefer, okay, let me see. In the next slide, we shall focus on the illustration for the current time step. Just assume that a corresponding illustration for the previous time step also exists. So, like I would probably try to avoid getting into these mathematical aspects because it will take much more time than I thought it will, or rather I've consumed more time than I had in my quota. So I will just skip these aspects. I will just try to say that we developed, and this was a novel thing which has been patented and which has been published also, the extreme adaptive critic algorithm for extreme learning machine. And then we will actually, I'll just skip these parts because I'm not sure how much has been understood so far. And this actually stands on the foundation that everything before this is fully clear. So let me just give you the final results. Here what we have is, as you said, the validation is that we compare across sufficiently long period of operation the value from the value of U when we are, U is basically used for prediction minded. So U from non-adaptive prediction, where I'm not adapting the value, and U from adaptation. And I see that the U from adaptation is significantly less than the U from non-adaptation. And at the same time, I'm doing it for ELM. So it takes 2 orders of magnitude less time and effort to do this adaptation. This is done on the same case that I did earlier for about 81 hours. Then we have taken a second continuous case for about 37 hours, 38 hours, and we'll see the same kind of results. U from adaptation is much, much better than U from non-adaptation. So to conclude, we have shown that machine learning techniques, both ANNs and ELMs, can be used for advanced prediction of adverse digressions in continuous time systems with reference to a noisy industrial process. In this context, we have shown that ELMs nearly provide similar accuracy levels as ANNs, but with significantly less training times. Industrial systems are prone to drift, hence real-time machine learning systems have to adapt online using adaptive critic systems, which involve repeated retrainings. ANN-based adaptive critic systems demand heavy resource loads, hence ELM-based adaptive critic systems, if they could exist, would be more preferable. For the first time, we have developed and validated ELM-based adaptive critic systems. Let me tell you, this was done 6 years earlier. Okay, so I mean, it is not that I have done it now and presenting it now, because after all, there's supposed to be exposition of application of AI in manufacturing. Returning to generics, the methodology developed, now this is very important, last statement. Returning to generics, the methodology developed here can be applied to predict adverse digressions in any non-stationary, or you can say drifting, continuous time systems. And we have seen that we had a whole lot of examples. We talked of financial systems, we talked of economic systems. In fact, we talked about metallurgical systems, geophysical systems, biological systems, electrical grids, or any kind of distribution networks. Okay, and we talked of vehicles, we talked of manufacturing. Within manufacturing also, there are continuous output manufacturing and discrete output manufacturing. So all of these can be, we have just instantiated this in one particular case. This can be applied in any other case as well. So this is the end of my presentation. Now I'm open to questions. We've got about 10 minutes, I think, but it's up to the organizers.
So thank you so much for your valuable insights. And I have a question for you, sir. Before asking for there are several questions asked by audience. And so, what was your struggle point when you have worked on this ML? You said that you have several experience in Tata Steel, Jamshedpur you have worked on, and you have given few of the examples over here, right? So, what was the most challenging part that you have faced while working on this?
Okay, so let me just tell you that this is a kind of ancillary to the main breakout prediction system that we developed. And like we had, see, how did we come to the adaptive critic system at all? So I had mentioned that this, if you want to predict in advance before the fault has actually occurred, we use machine learning systems, but they have to be very, very accurate and very fine-tuned, because we cannot err on either side. We cannot have too many false predictions, nor can we miss any true predictions. Okay, I mean, not true predictions, but any true faults, right? So we actually implemented this in a particular plant. I'll not talk about where. Okay. Now the thing is that when this was done, then after about a couple of months, I started having lot of calls from the operations that your system is malfunctioning and we are getting breakouts and we are getting too many false alarms and then that set me thinking that what is going on. And then we came to the whole, I knew in my abstract mind, I knew that there was something called as industrial drift. But the industrial drift, it directly maps into machine learning algorithms and it plays havoc with something that you have put, and it makes your life miserable if what you have installed is a critical system. Then we started developing these adaptive critic systems, and that took a lot of effort. So if you ask me, there are two responses to yours, or two instances. One is that when I learned the hard way that adaptive critic systems have to be installed, otherwise you cannot have, for critical systems, you cannot have machine learning models controlling them without adaptation, point number one. The second is that when we also tried to develop the adaptive critic system for extreme learning machine, because it did call for a lot of theoretical developments. So that, I hope I've answered your question.
Yes, sir. So we have a few more questions now.
So shall I stop
So
sharing my
machine
screen?
learning techniques for advanced detection useful in defense sectors, especially for threat detection? If so, what advantages do they have over traditional radar system and intelligence agencies?
Okay. See, this is okay. See, I think I missed some word. Can you just repeat this question once? Sorry about that. Hello. Hello. I think there has been a disconnection.
Yes,
Hello.
sir.
I
Yes,
think
sir.
you could just repeat the question, please. I think I missed some
Yeah.
parts of it.
So the question belongs that are ML techniques are techniques for advanced detection useful in defense, especially for threat detection? If so, what advantages do they have over traditional radar system and intelligence agencies?
Can you just read the last, what agencies you said?
Uh,
Intelligence agencies.
Intelligence agencies.
Okay, okay. See, one should understand that one cannot fit the same jacket on different systems. Okay, so in the case of manufacturing, you have a purely inanimate system in the sense, although it is dynamical, one is not there is no human at the back or intelligence at the back which is playing with it. All right. When you have threat perceptions, you have to appreciate the fact that there is always the adversary is always trying to maneuver or manipulate the system always. So if you make your system to be based on past conditions, and then you will not be able to get accurate predictions, point number one. Point number two is that whoever is trying to maneuver the system, your adversary, knows that or she should not allow you to learn how he or she is maneuvering the thing or manipulating the thing. All right. If you can learn how the manipulation is being carried out, then effectively you have beaten that person. All right. So you have to keep in mind that you cannot really apply this kind of adaptive critic systems to places where the adversary is trying to manipulate various things. All right. Maybe a simple example could be that, if there is an adversary, say missile, let's say, all right, which has entered your territory, and you have a counter missile which is going to go and hit it. Now that missile is maneuvering. All right. If that missile is maneuvering following some track, okay, that means you know how it is maneuvering. You can still go and hit it. But if there's an arbitrariness in the maneuver, okay, that there is something that is being done where there's a randomness, you will not be able to go and hit that. All right. So then the question arises that what are the time scales you are looking at? So then there are a lot of, it becomes a much more complex process. And if you ask me, I will say that one would not really like to have an adaptive system to learn the maneuvers of an adversary, because an adversary can make a fool of you in that case. Hello.
Yes, sir. Your answer well answered, sir. So we have, as you know, that we both are in the educational sectors, and we have a question on educational sectors. What challenges do educational institute face while implementing the AI technologies?
I don't know to what extent the question is relevant here. You see, for example, when you talk of AI technologies, So in my place, we have got a department of AI and computer science, and I have actually led this department for many years, and we actually created all the different curriculum and the different programs, BTech and MTech and so on and so forth. So as far as, see, I do not try to use artificial intelligence directly in class. All right. You can have face readers and all that. Okay, those things you can put up that, looks at the faces and looks at the moods of students and is able to predict various things. But if it comes to the curriculum and all that, there is, I mean, AI is AI. That's about it. Like any other new subject that is being taught, whether in mechanical or electrical or computer science, it is just like that. I do not really go into putting AI. See, there is a very small, I mean, I wouldn't really call it as AI. So purely in the attendance and the attention of students, you can implement some amount of AI. All right. Otherwise, it is just like any other course. I hope I could get through.
Yes. So now we have a most challenging question, that is AI ML often requires extensive data.
Yes.
But when we want to work on the industrial applications, industrial environment might have some data limitations. How do we overcome this constraint in industrial applications?
So this is the $1,000,000 question. All right. Now the thing is that if you go for, okay, now there are a number of things about this. One is that if you go for any of the large scale models, you will have to have a large amount of data. All right. So one would probably like to see, there are, I mean, one should not always chase something which is being flashed around in the media all the time. So there are large language models, there are very accurate deep learning techniques and all that. But to create those, you also need corresponding large amount of data. So looking at the amount of data that is available to you, you should try to create your model or choose your model appropriately. So there are a lot of models like, say, for example, XGBoost, or, like even ELMs, they don't require too much of input data, or there could be like so many other kinds of different models. Okay. So one can choose any of these machine learning models and they give fairly accurate results. We have generated very good results using, say, SVMs or XGBoost kind of models, or decision trees, random forests. We don't require too much of data. Having said this, now there are different ways of also manipulating or using low amount of data. One is that you can actually kind of recreate data from that which you have already got. Okay. So this is like boosting your own data, which you can do using different techniques. And I think many of you will be aware of that. The other thing is that what is called as transfer learning. Now, transfer learning, actually, you have to have a foundation model which is giving fairly accurate results. And then the important thing here is that the foundation model has to be from the same domain from which you are trying to use the sparse data problem. So you have a problem where you want to recognize certain things. Okay, let's say vision problem, and you have got some CNN which is trained for a lot of data on problems or data on neighboring kind of views. Say, for example, you want some specific kind of fault to be seen, and you have created a foundation model on large number of different kinds of faults. And then I think you will be aware of something called as transfer learning, that follows from the philosophy that when you have a deep network, the earlier layers, they actually learn the basic fundamental features, or you can say the low level features, and the high level features specific to a problem are learned in the last 1 or 2 layers. Okay. So what happens is that if you have a specific problem and you have a foundation model, then you just retrain your foundation model with your specific data cases, which are less in number, and retrain only the last or the second last layer. So this is transfer learning. So you've got transfer learning, you have the option of using different kinds of models. You don't have to go for deep learning models all the time. I hope you could
All right. Yeah. So we have one question from the audience. How
Yes.
can machine learning algorithm be used to predict equipment failures and optimize maintenance schedule in manufacturing?
So that is what I just see what I told you just now, gave you an example.
Yeah.
It is
Yeah.
actually
I think
predicting a
yes.
process, right? And let me tell you, predicting a process deviation or digression is more difficult than predicting the digression of a equipment like a motor or something. In fact, for many equipment like motors particularly, you don't even need machine learning models. You have got good empirical models which work well. All right. So fundamentally, basically you are recognizing that what is the normal condition, and then you are trying to also take up some examples of abnormal conditions, train the model on that. I'm talking of the ML based model now, and then you recognize when those conditions are about to come up. In fact, what I talked about in the entire example was that only applied to process rather than equipment.
Yes, sir.
I gave the example of capital UT, which is a function of VT squared, which is VT squared.
Yes.
VT itself is a function of how your ANN is predicting the normality versus what are the variables of that particular equipment process, and you need some amount of domain knowledge, which will, or you can say empirical knowledge, which will map the divergence between your prediction and the state of the variables in the particular.
Yes, sir. So there is another last question of today's session.
Okay.
Said that he is not a background from CSC, and so how can I tackle the issues of biased and data scarcity when developing AI and ML model? Because many data are not available when we are really working on the industry.
So, okay, you said that he is not from CC. By CC, you mean continuous casting, is it? Hello?
He's mentioning that he is from different background,
Okay, all right.
not
So,
from
see, this,
CSC. Yeah.
okay, not from computer science. See, this is always a problem. See, in anything, so you will, this is called as imbalanced data, all right? You will you'll never come across a situation where there are two classes and both classes are equally balanced. That can happen in theory, but not in practice. So what I would say is that, if with the balance between two classes, I hope the person is hearing this. If the balance between two classes is of the order of 70 to 30, just leave it as it is. Okay. Anything within that range is perfectly fine. It will work. Now the question is that when you have significantly worsened conditions, so let's say between say 85 to 15, one option is to try to increase. I mean, then in that case, you try to repeat your. I mean, you have to say, for example, you have got 1,000 data sets from normal conditions and just about 200 data sets from the abnormal conditions, right? So that would be something like 83% and 16% ratio. All right. So in this case, what you do is you try to reduce your net data from the normal cases, so bring it to 600, and then repeat some of the cases that you have picked up from the abnormal cases. So make it from 200 to 300 or 400 and bring it to the 70 to 30 range. All right. Now the thing is that if your ratio is as bad as 95.5, then it will not be possible to use machine learning models. Okay. Now what I told you, I didn't at all speak about something called as confusion matrix and something called as precision, accuracy, then precision, recall, F1 scores, and all that. So that is the reason why the accuracy term is not so much used when you try to judge the accuracy of an ML model. Rather, you use something called as F1 score, which automatically takes into account the fact that you have imbalanced data sets. But the question is, how imbalanced is imbalanced? So if you have up to 90-10, I think you can go ahead with all these imbalanced data sets using all these precision recall and F1 score. Beyond 90-10, you just have to cut down on your the bigger one. Okay, so that the ratio becomes of the order of 70-30 or 80-20. Okay.
So in relevant to that, I have one question. So
Okay.
how can we cut down the computation time? Because when we are working on the so much of large data set, like computation time will also increase. So is there any alternative way that we can cut down the computation time
See, there are,
of the
okay, to answer this question, please keep in mind something. Now, I suppose most of the people whom we are talking with have got some experience on ML models. So particularly, let's say for ANNs, like if you have an ANN, I'm talking of just a multi-layer perceptron, maybe having 3 layers or 3 hidden layers or so, okay? So it may take a few hours for training, but once the model is trained, it is just a set of matrix multiplications and application of activation functions, all right? And that is called as, so when you have the training takes time. When you have the inference, where you just put in an input data, pass it through the matrices and summations, and then the activation functions, it literally takes milliseconds. All right. So inference mode is not a problem for machine learning models in most cases, unless you have a very, very complicated model. All right. And in fact, there are, so in real production mode, you really work it in inference mode. When I talked about adaptive critic here, I had forced to do the training part also online, and that is why I moved over from ANNs to ELNs. So ANN models. So in that case, what you have to do is, if you really need to keep retraining your system, then don't go for very complicated models. You have to take an engineering view also. There is a theoretical view, there is a academician's view where I want to be as accurate as possible, and there is an engineer's view where I say that even if I get 97% accuracy, it is perfectly fine, because many other related systems are even worse in accuracy. All right. So I would just try to go for that kind of models which satisfy my engineering accuracy levels. Point number one. Point number two, please keep in mind that the actual inference takes literally milliseconds for any kind of model that I use, including ANNs, as compared to the time that is spent on training.
All right, so I think we can also go for MCDM techniques. There are other MCDM techniques, so that can also be justifiable in this process, right? So,
okay. There are lots of models.
Yeah. So overall, I think it's almost a time to wind up the session for the session one. And thank you so much, sir, for your valuable insights and the case study. And
Yes.
as you are telling that you are also traveling meanwhile, but you have spared your time and delivered the session, sir. So thank you so much for your.
That's my pleasure. I hope you also enjoyed it. And
Yes, sir. And we have got to learn so many things, and top of that we get to learn the real time thing that you have really worked on this, so that also inspired audience and also the faculty who have joined in this session. So thank you, sir, for your valuable time, sir. In future we'd like to connect with you, sir.
Absolutely fine. Thank you for giving this opportunity to speak to you and all your audience,
Thank you so much.
respected honorable audience. Thank you very much. Okay, bye bye. All the best.
Okay, have a nice day, sir.
Same to you. Bye bye.
Yeah.